The theme is how materials fail. Do they fail by bending or breaking in some sort of fracture? And it's a great pleasure to be giving the G.I. Taylor lecture, because G.I. Taylor is such a sort of hero to such a broad range of scientists, and famed for his elegant, simple experiments and his absolutely incisive analysis. So here we go. That's a painting of him aged 80. His entire academic career was at Cambridge, at Trinity, and the Cavendish. He came from an intellectual and well-connected family. His maternal grandfather was George Boole of Boolean algebra, and one of his great uncles was George Everest, that Everest. If you want to know more about him, George Batchelor wrote a really excellent memoir for the Royal Society on G.I.'s life. He did many things, but he's probably best known for his work on fluid dynamics. In the course of an active life, he published some 250 papers and reports, and a rather small fraction of those are directly relevant to today's lecture. But he was one of those people who seemed to be able to look in almost any direction and pretty much immediately make a serious, incisive contribution. This is what Wikipedia thinks he's famous for. You can see it's not a short list, lots of key topics, and his name associated directly with many of them. So that's quite terrifying. When he started his research, it was with J.J. Thomson on electromagnetic radiation and diffraction effects. He quickly turned to the sort of area that he's now more famous for, shock waves, turbulent eddies in the atmosphere, essentially dynamic meteorology. But a certain world event was approaching, and the British system was interested in airplanes. They already had the Royal Aircraft Factory. This, in due course, was to turn into the Royal Aircraft Establishment and be well known for its research. But at this stage, they were also making planes there. And GI worked there with a name which will be extremely familiar to material scientists in the audience, A.A. Griffith, well known for his work on the theory of the strength of brittle materials, that's to say, things that fail by cracking. And Griffith and Taylor worked together on propeller shafts, which had a key line along them to get torsional traction with the propeller. And of course, this was a source of failure. They worked out a design to reduce the rate of failure. They also worked out that they could only explain their findings if the metal in the shaft was actually changing shape. It was flowing in a plastic manner. And that presumably sparked GI's interest in that topic. So we'll be looking quite a lot at plastic deformation in this talk. So how would you do it? Well, to do it in a controlled way, you'd start with I have a little bar of copper here, we'll see it later. And you'd put this bit of metal into a machine. You would ask the machine to go upwards. It would pull it and stretch it. Now, if you imagine doing something like stretching a rubber band, you know if you stretch it a little bit and you let go, it'll go back. That's reversible and elastic. Well, with a metal, the distance of movement for that reversible elastic deformation would be far, far smaller than a rubber band, but it's still there. So you have this reversible elastic region. But there's a critical point, how far you pull it, beyond which it suddenly goes a lot further without you having to increase the force that you're exerting. So you have a change of regime from a spring-back mode to, at a force like this, continuing elongation of the part. And it does not then recover its original shape. So you have plastically deformed it. I need to explain to at least some members of the audience what is happening inside a metal when you do that, or what a metal is, because it will not be obvious to the general public that metals are crystalline. They don't look like mineral crystals, but inside they are in fact composed of an aggregate of lots of little crystals. We call them grains. If you were to zoom in on a given grain, you would find some very well-ordered arrangement of atoms. And that is a crystal, and it would look something like this. So you have a set of those, and when you deform this, you would like to know how it behaves. And G.I. Taylor probably pretty soon figured out that he wasn't going to make much progress if he tried to solve everything at once. And indeed, the proper place to start was by looking at how you would plastically deform a single crystal. So imagine you could cut a little bit of this out, then you wouldn't have all the complication of those junctions. Well, this is his great paper on this. G.I. working with Constance Elam. Those of you who were very eagle-eyed would have seen on the list of Philosophical Society lectures in that yellow display before my display went up, in the bottom left-hand corner, a mention of the Constance Tipper Lecture Theatre, where a certain set of presentations on Maxwell will be at the end of term. Well, Constance Tipper is the married name of Constance Elam. She was at this stage working in London at what would now be Imperial College, growing single crystals, and these were what was used for this work. So what happens if you take a single crystal and you deform it? Imagine a piece of metal that might have a rather polished surface. You then deform it and it looks like this. What is happening, of course, is that the crystal planes are slipping over each other, and they thereby make slip lines on the surface. So that was what was going on there, and they, of course, were wanting to do it in a way, Taylor and Elam, that could be analyzed. And here are a couple of pictures from their paper. So this is a schematic of one of these single crystals. Astonishing feat of crystal making. These, in the real world, were square cross-section bars, where the sides of the cross-section were 1 centimeter, and the length of the crystal was 20 centimeters. Astonishing, single crystal. And the way they were made meant that you got a random crystal orientation every time. That, in one sense, was awkward, but in another sense, wonderful, because it enabled you to test the effect of angle with every experiment you did. And of course, that then meant relating the sides of the crystal to the angle of those crystal planes. And I put in this diagram just for the amusement of some in the audience who've had to go through all of this in their undergraduate lectures of tensile axis moving towards whatever in these stereographic projections. They needed to use those to understand what was going on. So from this work, we have a really secure understanding of what it is that is moving in the single crystal when it deforms. There is, however, a problem, and it's a pretty big problem. That is, if I take a crystal and I stay in the elastic regime, I can push it a little bit, and it'll have a resistance to that, and I can measure that as an elastic modulus. It will then just spring back. But the value of that elastic modulus should be a pretty good guide to how hard I have to push to get the plane to actually move irreversibly. And when you do that calculation, you get a set of predicted strengths, if you like. And here they are in megapascals. And when you measure the strength, these are the values you get. So what it's saying is that we thought we had a really secure model for predicting the strength, and it's predicting a strength some 1,000 to 10,000 times higher than the actual strength. So there's something desperately wrong. And that would undoubtedly have remained a point of interest for G.I. Taylor. In a separate paper, he spotted something else, which is highly important. So here again, we've got one of these, if you like, force extension curves. And the elastic region is now here. The fact that that line is pretty much vertical tells you that the elastic deflection is tiny. But once you go into the plastic regime, the material just keeps going. And if I were to do that with this copper bar in tension, this particular bar would extend its length by 30% before it would finally break. And that's that plastic flow. But as you get it to flow more and more, you have to exert more and more force. And that force has a very characteristic shape, and it shows up again and again. So the the force you have to exert increases not linearly with the extension or strain, but roughly as the square root. So it's called parabolic hardening. That increase is thing we would call strain hardening. And I want to get across the point that this is immensely important for the world of metals. Imagine I have my metal and I pull it. As I said, with this copper, I could pull it about 30% and it would remain actually uniform with parallel sides. But more likely, something will go wrong. And that would be, well, once the material starts to get thinner, if it didn't harden enough, it would continue to get thinner. You would call that necking, and the material will rapidly fail. It won't allow you to go to that 30%. The reason you can go to the 30% is that if it started to get a bit thinner, it doesn't just get thinner, it also gets harder. So it protects the material from further flow there, which forces the flow to spread through the whole bar, which is why you get the uniform flow and the ultimate extension. So this strain hardening delocalizes the strain, it forces it to spread, gives you homogeneous flow, it suppresses this necking, which gives you the property called ductility, that's that 30%, and of course that all helps to suppress catastrophic failure, and that gives you reliability of your structure. So we could say strain hardening is really why metals are such good structural materials. It's not that they're hard, in fact they can be rather soft, it is that they can harden. It's the hardening that makes them really important. I should say, of course, that once you know the mechanisms, you can do something about this to make them harder to begin with, but strain hardening remains a really important thing. So here is this paper, and G.I. Taylor knows that after we have deformed the metal, it is harder. He thinks, well, that must mean there's been some sort of structural change. The material in there is different from how it was to begin with. They didn't really have a clue what it was. Their one assumption, a prominent assumption, was that when you slip these planes, that, of course, it in some way disrupts the crystal structure. And they assumed that you could have formed layers of amorphous material between the slipping planes. And that would act as a sort of gluing up of the system that wouldn't allow them to slip. We now know that that's not the explanation of what he was seeing, but you can actually do this. If you take a crystalline metal and you deform it heavily enough, you will eventually destroy the crystal structure and you can form an amorphous metal. But that was not what was going on in his case. I want to reiterate that the idea that when you deform the material it gets harder is quite remarkable, because it seems a bit counterintuitive. You would think you would be in some way destroying the original structure and weakening it, but the opposite is happening. You'll note the title of this paper is about the heat, because Taylor was also fascinated by, well, if you're getting some sort of structural change, that must be reflected in the thermodynamics of the material. The heat content of the material must change, and this paper set out to measure that. We wind on 10 years or so, and 3 people, Egon Arawan, Michael Polanyi, and G.I. Taylor, in the same year, entirely independently, have the same idea, which is a geometrical construction recognized by Vita Volterra called a dislocation. Needn't just be a static thing, but could move through the material, and that would explain why the strengths were a factor of 1,000 or 10,000 less than predicted. This is Taylor's diagram of it. He might have had in mind a model something like this. Experts in the audience will be well aware that you don't normally find crystals with this particular arrangement of atoms. We could argue there is polonium that has this structure, but I wouldn't want to be this close to a lump of polonium. But the point I'm making is that in order to get, in a sense, the right answer, G.I. Taylor didn't need a particular structure. He just needed any structure that was simple, and he was thinking about a dislocation of this kind, but you will be interested, those of you who know about dislocations, is that this paper is well before any mention of the concepts of edge or screw. And you'll see he's talking about positive and negative dislocations, something we don't normally refer to today. But the idea is that you would force in the side of the crystal, generate this step, you then have a crowding here, but that could migrate across and pop out the other side. GI described it as an insight based on his work with Griffith, which was on cracks. Now, normally when you have a crack in material, we think of it opening up. The two things come apart. But you could have a crack that operates this way, a shear crack. And he thought, well, if you have a shear crack, the atomic bonds that were here could stitch up again after the movement. So you could restore an equally perfect crystal structure. So this is just as perfect as this. It's just that it has, of course, moved sideways. So you have a permanent change of shape. So we could say that these three people have something like equal credit, and they certainly deserve equal credit for the concept of why this makes it easier for the crystal to slip. And one of the standard analogies is if you had a sort of rubbery rug on the floor and you tried to slide it along the floor, you'd have to pull pretty hard. But if you scrunch up one end and make a rug, that will travel really rather easily, which is saying most of the time, most of the rug, and therefore most of the atoms in our crystal, aren't actually doing anything at all. All the action is just along this line, and the line is rather easy to move. So far so good for the three people who were doing this independently, but in one respect, Taylor went far beyond the other two, because he was the only one who then thought, well, this will help us do the strain hardening problem. How is it that the metal becomes harder? And it is that as you deform, and here's our parabolic curve again, you generate more dislocations, and dislocations get in each other's way. And you have a characteristic drift distance of a dislocation. And once you put that length scale into your problem, it's just a dimensional analysis, and it all falls out beautifully and rather simply, that you get this parabolic hardening. So that set the scene for how you would interpret this phenomenon in metals, and you can do a lot with it. And I've said that the actual strength of the metals might be a 1/1000th or 1/10,000th of the predicted strength. Well, you don't have to have such a big ratio. If you design things well enough to interfere with dislocation motion, you can make your real metal much harder. And so piano wire is probably about 30% of the ideal strength, not 1/1000th of the ideal strength. So you can move on a lot. So the next bit of the talk is to now turn things around and say, well, courtesy of G.I. Taylor, we might feel we have a pretty good understanding of metal flow and hardening when the metal is crystalline, which of course usually it is, but this probably leaves us a bit at sea if this is your structure. So this is obviously a computer-generated image of a solid. It has three elementary components, and it is clearly not a crystal. I will not go into this, but it's actually quite highly ordered. But it doesn't have crystalline order, and in particular, of course, it has no well-defined planes, and those planes were the things that were doing the slipping for us. But before I get into how the glass does its deformation, we should look again at the crystals, and I have Ambrose to help, I think. So Ambrose is going to tell us, or show us, about the phenomenon of work hardening in the crystalline metal. So it's our little bar of copper, and Ambrose is going to bend it pretty much double. Ugh. Right, good. So he's done quite a good job. So I will now switch to my visualizer. And our formerly straight bar is now like that. And now I'll ask Oliver to bend it back. He's done a pretty good job. We should congratulate Oliver for doing so well. But it did require a lot more force. So how do we make a material like this? We could start with a liquid. Where did I put my pointer? Oh, here we are. Start with a liquid. You get down, cool it. It, of course, shrinks a little bit. This is the melting point. So below this point, it should freeze into a crystal. But if you're lucky, you can keep going. You might have to go rather fast. And the liquid becomes more and more viscous. And eventually, it sets into a solid, which has essentially the structure of the liquid, but the mechanical properties of a solid. We would call it non-crystalline or amorphous, and if we make it this particular way, I would call it a glass. And it has properties down here. So the point I want to get you thinking is that a glass, in this way of looking at it, doesn't rely on it being a particular chemistry of material. You are familiar with window glass, wine bottle glass, etc. But you could make glasses out of pretty much anything. And it, for a long time, was not considered that you could make a metallic glass, for the reason that these crystal structures are so extremely simple. So obviously, they can form very easily in the liquid. But you can make a metallic glass. You have to avoid the crystallization or freezing, and you get a range of states depending on how fast you cool. We'll come back to that concept. I mentioned that you might have to cool rather fast. This is an example of a rapidly spinning wheel, hot liquid coming onto it. This ribbon comes off. It's a few tens of microns thick. And the cooling rate is anything from about 1,000,000 degrees per second down to 1/10 of that. So pretty fast cooling. And we should think, well, does this do anything for us? Well, this particular material, which comes off iron-based, remains the most important commercial application of glassy alloys. I should say they are metallic, so you will not, it's not like a see-through glass. It looks entirely metallic. This is the original stuff, and there are various variants on it here. This is a soft magnetic composite of little glassy bits embedded in a resin. Great variety of electrical applications, but most notably in electrical transformers. This remains the biggest market, and it's very, very topical. So this is saying you want these soft magnetic materials. They're not good permanent magnets. You can magnetize and demagnetize extremely easily, and you can reverse the direction of magnetization extremely easily, so they're very good for low losses in transformers. You can use them in transformers, but you can also use them as inductors, as that table on the previous slide showed. And these are made in massive quantities, especially now as 5G phones are coming on scene, where you need ever more of them. So you probably are the proud owner of several of these little bits of glassy metal without knowing it. They're embedded in your phone. Where they're more obvious would be like this. So this is a rather awful looking sort of distribution system for electricity that you would typically find in the United States and Japan, not in Europe. These are the local distribution transformers, changing your voltage down for local use, and they have these cooling fins. They need the cooling fins because the transformer core inside dissipates a lot of energy. And it's because the grain-oriented electrical steel isn't as good as it should be in allowing you to keep switching the magnetic field direction, magnetic moment. So there's a lot of energy lost in these. This is the material, grain-oriented silicon steel. And there's much interest, and has been for decades, in changing to glassy or amorphous, as they're saying amorphous steel. That's our thin ribbon I was just talking about. This is of considerable political interest. This is from the briefing notes for the US Congress. And they're talking about this amorphous steel and how they should be pressing for its use in order to reduce energy loss in the transformers. And if this were adopted across the whole system, ideally, you'd save a very high fraction of the energy loss in the core, but in cores as they're made in practical terms, you would save about half of it. And half all of the transformer loss across the US, of course, would be an enormous amount, and you're talking easily billions of dollars per year. So the Biden administration considered for some time mandating that the electrical distribution in the US should be exclusively using amorphous metal cores. And it was easy to calculate that that would be an enormous energy benefit, blah, blah, blah. Unsurprisingly, it hit a bit of resistance for multiple reasons. You've got the standard pork barrel politics, where if the senator has a manufacturer of grain-oriented steel in his backyard, they're not going to want that to be put out of business. There was also the point that although the thin amorphous ribbons were developed in the US and first manufactured there, there's almost no manufacturing there now of them. It is, guess where? China, which of course is busy using them for its own distribution system very effectively. So the law was changed, or it never became law, but the intention was changed to mandate that the prices would be set that would allow good business opportunities both for the traditional material and for the amorphous material. And I suppose now with a change of regime in the White House, perhaps the boat isn't just rowing in the opposite direction, but perhaps has been destroyed. Very big news, because this area of saving energy as we go more and more electric is very important in the energy transition. Those were thin ribbons. Could we make a metallic glass in greater bulk? Well, you can if you mix enough different elements in. So this is quite a complicated formula. The point is the poor system just becomes confused. What sort of crystal can it make when it's trying to put together so many particularly different sizes of atoms? And you can get the critical cooling rate no longer 1,000,000 degrees per second down to maybe 1 degree per second. And since it's so slow, you have plenty of time to get the heat out, so you don't have to be thin. You can have it in bulk. And this just gives you a timeline for the maximum diameter. Here's 7 centimeters. They're made fully glassy. This just shows that once you've got one of these bulk things, you can do simple experiments with it. And we've said that you make the glass in the first place by coming from the liquid. So you cool the liquid and make the glass. So if you have the glass, you can heat it up back towards the liquid state. And this is a fun one where the transition temperature is below the boiling point of water. So in warm water, you can put your metallic glass bar and bend it extremely easily. It's thermoplastic forming, and that allows you to do all sorts of things that you wouldn't normally think of doing with metals. So we're essentially doing glass blowing, but no longer with traditional glass, instead with a metallic glass, which, as you can see, looks nice and metallic. I should explain this is from a laboratory in Yale, so this is an imperial inch. And probably you can see Professor Schroer's in the reflection with his own camera. It allows you to do sorts of things that you never thought you'd see with metals. These, of course, are not commercially exploited, but it's a demonstration of what can be done with a metallic glass and the forming ability. So let's think now, what can we say about the strength of these materials? So you don't have these crystal planes sliding over each other. And we said that with the intervention of dislocations, sliding over was actually rather straightforward. So we could imagine that possibly the plastic deformation, the strength or hardness of these glassy materials will be higher than the crystals. And so it turns out to be that if you compare them across the range of essentially all known categories of metallic materials, they're the dark ellipses at the top. This is a logarithmic scale, so this is quite a big difference. But would you really notice the difference? Well, that's our next question. So what I have here is a block of steel. I should put this in the middle perhaps, but actually, well, I'm not sure where to put it because actually the best view will be from the front rather than in the visualizer, but the visualizer lights it up. And is this hard and resistant to indentation? Well, we could test it, so I'll just take an ordinary ball bearing, and I'm going to try something delicate here, which is to reattach my mic, or bring the microphone close. So not much return of energy, not very exciting. We now say, well, let's do this with a metallic glass. And there's a metallic glass plate on top of this. And we'll now see if we can spot the difference. So I will argue there is a marginal difference in performance, which you might be able to spot, and that, of course, you could put to use in all sorts of ways. And one way to think about that is that if you wanted to store energy elastically in a material, it would be the area under this curve. This is the force converted into stress and the extension converted into strain. So the area of the triangle is how much energy you would store. How would you increase that? Well, you could make the material stronger, so you would simply go up further. The thing that probably you could easily get wrong is thinking, well, how elastically stiff should the material be? And you would probably think that, well, if you make it elastically stiffer, you must be able to store more energy, because after all, you have to push harder. But of course, if you reduce the elastic modulus, you increase the stored energy for a given ultimate stress, as would be seen. You can easily store energy in a rubber band, for example. So this is something underlying the behavior you just saw, that we can store more energy if the material is more resistant to plastic flow of those strains. You can simply go higher without making an indentation, and it helps that it also has a lower elastic stiffness. Now, so far that sounded pretty good, but there can be a bad aspect to it, and that is we think, well, if the flow of the material is too difficult, could it be that the behavior is really like conventional glass? After all, this is very hard. It's very scratch resistant. It's arguably quite strong. It doesn't flow easily at room temperature. But it does have a drawback. And the drawback, Gabriel will now demonstrate. Good, thank you. Oh, thank you very much. So, glass is brittle. So, should we think that our metallic glass will be brittle? Well, we know that the glass of a wine bottle or whatever, it lives here on this diagram. This is the strength. So in terms of its hardness, how hard it is to get to flow, it's up high on that scale, but it's very low. Indeed, it's at the bottom on this scale, which is a thing called fracture toughness, which is the resistance to cracking, which is what Griffith was interested in. So where does a metallic glass sit, and how should we look at this in general? Well, in general, to avoid failure by cracking, you need to get the crack to be blunt, and that means you need to get some plastic deformation. So you more or less have one or the other. And this is the typical trade-off. Some people will be familiar with how this works for steels, where you could take a hot steel, quench it, you get something very hard called martensite, but it's also brittle. And then you anneal it, you temper it, it becomes less hard, but it becomes more tough. So you have one or the other, basically. You have a trade-off. Interestingly, if you say, well, can you tell me of all known materials, which has the best, highest combination or highest product of the two things, yield stress and toughness, it is in fact a metallic glass. And that's the property we could call damage tolerance. So we do not need to worry about them cracking in the way you just saw. There is still a problem, though, that when you deform them, they don't deform smoothly. They look like this. It's telling us that unlike our crystalline metals, the flow is now localizing. It's not delocalizing. So this is work or strain softening, not strain hardening. And that's desperately bad news. These shear bands are a remarkable phenomena in their own right. They're utterly clean, not a hint of a crack anywhere. But when the material is in tension, they spread across the cross-section, and you get, after the elastic region ends, you just get fracture. So our ductility is not the 30% of the copper bar, it is 0. And that would generally be thought to be bad news. To give you a sense of how remarkable they are, this is a bent metallic glass wire, lots of these shear bands. They're, of course, very unsightly, which is one problem. If you were making some component, you wouldn't want to have these surface markings on it. Of course, when this bar was bent, it was then allowed to spring back. And here's a little bit that obviously lived between two shear bands, and when it was springing back, popped out, which is saying that the bits of metal could slide extremely easily relative to each other. The actual width of a shear band from microscopy is taken to be about 10 to 20 nanometers, and that probably applies in the early stages. Then you get to something like this, and then the thing comes apart. The fracture surface is quite remarkable. It's this so-called vein pattern, which I can now reproduce for you, I think. I'll give myself a black background. And we'll take a glass plate. And we'll take some hand cream. And we'll take another glass plate. And I pull them apart. And I get a vein pattern, just like would have been seen in the metallic glass. And it's one, of course, that would be very familiar to G.I. Taylor. He used a Healy-Shaw cell, thin cell. You fill it with two fluids, one more viscous, one less viscous. The original area of interest was how to get oil out of oil wells in porous media. Could you push it out by pumping in water? It turns out you can't very well, because the less viscous medium, in that case water, doesn't push the oil ahead of it, but fingers into it. It does tell us that oil would be an excellent way to get water out of water wells, but that's not normally what people want to do. In this case, the two media were not two liquids, but a gas, air and glycerine. They're pumping glycerine in from the top. This is a thin plate shape. When you look through, this is the original boundary. And as you push the air in, it doesn't push the glycerine on a flat front, it starts fingering in. And that's what's happening exactly in this liquid-like layer of our metallic glass. And that's been analyzed, and it tells us the liquid layer must be quite thick. But why does the thing liquidize? Is it heating up, or is it something else? Well, you could, of course, think what happens when you force something to shear. And in this case, with a crystal, if I force it to shear, it fits just as well afterwards as it did before. That was Taylor's point. But if it's not crystalline, if it's glassy, then of course it won't fit the same if you move it over. And that's exactly the phenomenon happening here. So this is somebody walking on a wet beach. You'll detect that the sand goes dry around the footprint. That's because when the sand is deformed, the grains have to move over each other, and the system as a whole has to expand, so that the aggregate of sand grains occupies a larger volume around the deformation, but it still only has the same amount of water in it, so it actually raises the sand proud of the water. There isn't enough water to keep the sand equally wet. And it's an expansion due to some local rearrangement. Well, that could be perhaps what's going on in our metallic glass. It was proposed. Or it could be that this liquid-like layer really does reflect heating. Well, existing measurements and predictions were haywire, and no good guidance at all, so we thought we could try and do something about this. And it was to say, well, how are we going to detect this local heating, if there is any? We will take the metallic glass bar that we want to break. This is macroscopic, it's several centimeters. Notches, you deform it, but on this surface we have applied a coating of tin, which would look like this. Tin, of course, is a low melting point. That's the key part of the story. And we verified with a laser flash that when the tin does melt, you can detect that it is melted because you get these droplets. So with that as a background, we're using the tin as our detector, and it's a wonderfully good detector because you can work out a typical time for things to happen, the thermal diffusion time, so it gives you your time resolution of our heat detector. And the scale of this gives us essentially a spatial resolution of our heat detection. And those compare extremely favorably with doing it by direct measurements using infrared. So people have been doing this, but this is streets better. And I like to think that possibly of anything I've ever done, this must be the experiment that might be closest to one that would actually interest G.I. Taylor, because it's just a nice, neat little thing of letting the tin do the work for you. And what happens is it does indeed melt around the shear bands in a place like this. You get a distinct zone on this is the top surface melting, and what we need to do is measure the width over which the melting has occurred. That can be related to a thermal spike, and this heavy line is what we think is the shape of the temperature profile at the point where the melting of the tin has gone to its maximum extent. So this is where the shear band is. Remember that in relation to microns, it's only nanometers. So out here, the coating never reaches the melting point of tin, and here it exceeds it. So this we would think is where it gets to as a limit. You can put some numbers into this. We'll ignore all the detail, but just say, seems there's no relation between the thermal diffusion length and the thickness of the shear band. So we would conclude that the shear softening is a cause of the local heating. Once you localize things, you concentrate where you get your heat, but it's not the consequence of local heating. What's the consequence of is the shear dilation. However, it's left me with the obsession of how to get strain hardening in a metallic glass. We've so far miserably failed to do that. Well, you can get a range of glassy structures. We know that if you anneal a glass, it goes down in energy. That's called relaxation, and that can make the glass, the metallic glass, more brittle. So you actually want to go in the opposite direction. And because it's not relaxation or aging, it's called rejuvenation. You could apply lots of mechanical processes to do it and bump up the energy, which would be rejuvenation. This is a little schematic of cooling the liquid into a glass and saying, well, if you cool it faster, you can get a glass with a higher energy. So maybe you could use these processes to mimic faster cooling. And it turns out you can. And if you put it to extremes, you can make the glass, if you like, think that it was cooled by quenching at 10 to the 10 Kelvin per second, when it was actually cooled at 10 to the 2 Kelvin per second, in terms of modifying its structure after it was formed. And I'll skip through these slides to take us straight to this. When you get the shear band, the force you have to exert goes up and then it drops. This is our strain softening. But if we think of this not in terms of the strain, the amount of movement, but how fast you are straining, then it would look like this. This is now the stress strain rate. And the curve looks like this. Key point is, for a particular stress level, it's double valued. You have a low strain rate outside the shear band and a high strain rate inside the shear band. And we need to get rid of that if we want to avoid shear softening and the formation of shear bands. And it seemed to me one way to do it was to soften the glass to begin with. You could then imagine a smooth rise, and you'd hope to get strain hardening and to eliminate shear banding. Wasn't clear that it would be possible because it has to be a very extreme treatment of the glass, which might lead the glass to be unstable with respect to things like crystallization. But it can be done, and the way you do it is you have a cylinder of bulk metallic glass, you machine a notch in it, you then compress it. The material of the notch is highly deformed, but doesn't, well, it's deformed under very high stress, but the actual strain is tiny. And amazingly, it becomes less dense, although you're compressing it, and that's this shear dilation phenomenon. If you can measure this is in a cross-section, measure the hardness, it gets about 36% softer as a result of this loading. And there's enough volume, this is 2 millimeters across, so you could actually cut out the entire softened volume, which now becomes our sample for testing. And here you have classic strain hardening. Loading, unloading, reloading, resumes at the same point, gets harder. You'll say I'm cheating because that's in compression, and the real test is in tension, but it does the same in tension. So we have a strain hardening metallic glass. We can look at the diffraction pattern, and that evolves to tell us that the material has become less dense, although it was compressed. This is stored energy. So what happens with these pink arrows is the effect of our processing in that notch cylinder. We drive the hardness down, we drive the energy up, and we drive the material to lower density. And then, that's our starting material. When we deform that, it tries to revert to its original condition. So the hardness goes back up. That is our strain hardening. The energy comes down, and it becomes more dense. This is sort of neatly the opposite way around from G.I. Taylor. So G.I. Taylor's deformed specimens have higher defect density and higher energy. Our deformed specimens here, deformed after the pretreatment, are the other way around. They have lower energy and lower defect density, but they do harden. So if you have no pretreatment, as soon as you compress this cylinder, it forms shear bands. But if you do the rejuvenated one, you can get to nearly 3% strain with not a hint of shear banding, and it's true plastic deformation. So you really do eliminate shear bands with appropriate treatments. The material does get harder, and you could ask, well, how fast does it get harder? It's hard to see the onset of plastic flow here, but it is here. And the answer is that it gets hardened much harder very fast. Much harder than many conventional materials. This is an ultra-fine-grained steel, which is roughly competitive. Why does it harden so fast? Possibly because every atom in that structure has its little job to do in making the material harder, unlike just those at dislocations. This is the hardening rate. The red line is for the bulk metallic glass in tension. Hardens enormously fast compared to conventional materials. And the wise people in the audience will realize this is, of course, actually bad news, not good news. Because if you're hardening that fast, you can't keep it up for long. And the real good news would be to spread the hardening out over a longer time. I will skip the details of this. Metallurgists in the audience will be familiar with the constant air construction. But it's a way of predicting what is that elongation we could get, the so-called ductility. And I already mentioned that for copper, it's 30%. For our metallic glass, it's at best about 1%, even with the hardening. So we got strain hardening, but there's work to do to make it a more useful strain hardening than we have achieved so far. So we're limited to about 1% ductility. I'll close the talk with a series of quick slides to give you an idea of where's the world of metallic glasses right now. So it started with thin ribbons. Those are the million degrees per second ribbons that are used in the transformer core. There was interest in going finer. This is a pure metal glass made at nano tips, and the cooling rate of that is about 10 to the 14 Kelvin per second, so 100 million degrees per second. There's interest in getting fine patterns on metallic glass surfaces, molding them into gears. These are pressure gauges. That's perfectly recognizable, and another gear. Much of the interest in the field has been how big can you make them? And the thinking has always been, well, to make it fully glassy and big, you must take a long time to get the heat out. So your cooling rate will be low, and that'll be a problem. But if you can do additive manufacturing, where you build the material up from powder layer by layer, you throw away that size constraint, because every layer is quite rapidly quenched, and so you don't have the link between component size and cooling rate anymore. That opens many doors, but it's fair to say there are many issues with the quality of that material, but very active research area. Those ribbons that you used for the transformer, you could turn into wave springs. You could compare them with commercially available crystalline wave springs. And the fact is that to support the same load, they're just 1% of the weight of the crystalline spring. And you can support over 1 million times their own weight. So a fantastically increased performance by using the glassy material. And Costas, is part of this work, is in the audience. Of course, you'd probably more likely apply it on a micro device scale, where you've got nice springy action. The glasses allow you to pattern the surface. That could be of optical interest, but there's increasing interest in developing surface patterns that program the interaction with biological cells. So you could promote cell adhesion, you could promote the death of inappropriate bacteria, etc. Very active research area just from the fine-scale mechanical pattern. At the time of this slide was made, this was the world's smallest electric motor. Its diameter was 1.5 millimeters. They've now taken it down to 0.9 millimeters. Inside the circular casing, you've got a whole sun and planet gearing mechanism, which tells you the gears, of course, are even smaller. And it's of interest because the metallic glass gears last a lot longer than the tool steel gears that were used before. And of course, lots and lots of uses for such a fine device. These gears are not so small, but they're vital for NASA. It turns out that a major part of energy consumption, for all I know, it might be the major part in things that have to have moving parts in space, is the energy you have to dissipate in heating the gearing systems so they work, because they are lubricated, and of course they won't work if they're at the temperature ambient in space. The metallic glass gears work at any temperature, and they don't need the lubrication, and so you save an enormous amount of energy. These, of course, are on the market. You'll need quite a lot of money if you want to buy one, but they're very attractive, scratch-free, and some of you will know that this is the favored brand of James Bond. So this has metallic glass in the bezel. just to say I don't want to persuade you to buy from a particular supplier. These are used in several luxury watch companies. It's of interest that they put BMG, bulk metallic glass, in the name, and I have a little story about that. Most of the companies commercializing these things rigorously avoid the use of the word glass, because for most customers, including industrial customers, glass immediately makes them think of glass bottles. So they assume that a glass must be intrinsically brittle. So they're usually called amorphous alloys, or, as you'd have seen from the watch previously, liquid metal is the way you would describe it. They are nice and scratch resistant, and this shows a hallmark standard 85% platinum glass bouncing on the floor. It's a little platinum cage about 1 centimeter in diameter, and the sound wasn't working, unfortunately. But as it bounces on a ceramic tile floor, it sounds like a rubber ball bouncing, not a metallic ball, and that reflects the properties you saw earlier of this bouncing, where it has high yield stress but a rather low elastic modulus. So this is not yet widely available, but will be highly attractive for jewelry, because while you might not need the bouncing quality, you would certainly appreciate that it's very scratch resistant and the hardness is much higher than the crystalline metal counterparts. The other place, apart from inside your phone where you might have metallic glasses in your ownership, is something like this. So these three-way foldable phones are now the hot thing in China, Huawei phones, and their hinges are made of metallic glass. This is an example of one of the hinges. They need to be extremely hard, wear-resistant, and extremely accurate in dimensions. And you can mold these directly to the final dimension that you cannot do with crystalline metals. The reason is simple. You form the glass from the liquid. There is no crystallization step. So you don't have the shrinkage associated with crystallization, which leads to uncontrollability of shape. When this slide was put together in the summer, approximately 80 million of these had been made by a single Chinese company. It's presumably an altogether higher number right now. So I think our sort of personal obsession, if you like, was, can you get strain hardening in metallic glasses? The answer is yes, you can, but it might not be as useful as you'd hoped. And a concluding slide is, well, of all the topics that G.I. Taylor worked on, I touched on only 3 of them. But there would be other possible points of contact with the shear bands in metallic glasses. Many people think they have some type of vortex at their tip, and GI would undoubtedly have been interested in those. So thank you very much.